Hi everyone, thank you for having me here. My name is Suanming Mou. I'm from NVIDIA. So today I will share some user experience regarding unified representer with large-scale ports. Okay, so before introduce the optimization with unified representer, first I will try to introduce some background regarding this optimization, in case you guys someone may not be familiar with the DPDK switch model. Okay, so typically for now in DPDK, if you are in switch model, if you are using the switch model, then usually let's focus on the bold line, the black bold line and the red bold line. So usually if the packet, once the packet comes from wire or the packet sent by VM, okay, so if the we will have some flow rules in the eSwitch FDB, yeah, the forward database. We receive some hardware offloading rules. So if there's no rules in the hardware, then the packet will miss. So it goes to the blackboard line. Okay, so the behavior is something like that. If the VM if it miss from VM 0, then it will miss to the VAF 0 represent. Okay, if the packet miss from the traffic comes from wire, then it will goes to the uplink. Okay, so that's the default behavior. And the packet miss means that it cross from FDB to NIC-RX domain. Okay, it just cross domain. So meanwhile, then for the application in hypervisor, when it receives the missed packet, the application will check where it comes from, and based on the logic, it will offload some hardware flow rules to the hardware. Then for now, we will have the hardware flow rules. So next time when the packet comes, okay, it will just hit the hardware flow rules. Then just like the red bold line showed, it will go to its destination as expected. So the application will not need to handle the packet anymore. Yeah. So we call the missed case slow pass, and we call the hit pass. The hit pass called the fast pass. Okay, the hit case. That's it. And then let's go to the next slide. Okay. So like we talked, for the slow pass, packet will miss from wire and received by a application. Okay. And for the fast pass, application will be bypassed. The offload rules will handle the traffic. Okay. So here comes the challenge. Think about that. For nowadays, usually we will have a lot of VAFs or SAFs. Think about that. Maybe we have 100 the K of 1K sub-functions or VAFs. So in that case, that means if the packet miss from hardware, then you will need to, for the application, it will be needed to polling, like the modeling we just introduced. It will need to polling all the represent ports to understand, to get the missed packet. Okay, let's go to next slide. It will be something just like that. So if we for call 0, usually we need to prepare the queues for all the represent ports. So every queue typically in OVS, we need to call 0. We are polling in this example, it will polling all the represent ports Q0 to get the missed traffic. And same for call 1 and call 2, call 3, etc. Okay. So think about that. If we have a lot of represents, it will be a disaster, and the CPU will be busy with polling the missed traffic. Okay, and preparing the queues for this represent port will also consume a lot of huge page memory. Okay, so yeah, so the challenge of large number represents usually like the picture just showed, n cores and n queues each port, and the core X pulls QX of all the ports. Okay, Yeah, so think about that, the high memory consumption. Yeah, it will take around, in this example, 1K staff and WAF represent. Okay, it will, in our case, it consumes almost 12 gigabytes. Okay, so and in that case, this will also cause the high CPU usage, high cache miss. Think about that. You need to pour every port, right? So the cache get flushed, and when porting so many ports, it will cause low performance. Then it will cause high latency in case. Okay, so since CPU handles traffic not offloaded, right? The slow pass packet. Even if our packet comes from one WAF, and the OVS must pour all ports in case to not miss any packet. So since we don't know where the packet missed from, yeah, so we must pour in every port. Okay, so let's see how we can optimize that in our Mellanox 5 PMD. Okay, so like we just showed in the first slide, usually by default, the packet missed from VM X will miss to WAF X, the WAF represent X. Okay, so in fact, this is controlled by dev arg called the representer matching. That means, and this dev arg was enabled by default. It's set to 1 by default. So if representer matching is 1, then that means the internal flow rule will steer the packet to relevant represent port, just like we saw in the first slide. Okay. Then the plan is to set representer matching equal to 0 to disable that. And meanwhile, after this dev arg be disabled, then the flow, all the packet. Okay, just let's focus on the black border line. All the packet from WAF, no matter from WAF, which WAF, it will all goes to the uplink represent. Okay, we can receive all this packet from uplink represent. So in that case, no need to pour in the WAF represent port anymore. Okay, then here comes the problem, how we can understand if we pour in only the single port, then how we can understand which source port the packet is when it meets to the represent, the uplink, the single uplink represent. Okay, so in that case, so we will offload the rules, let rules to copy the source port ID information to the packet metadata. Okay, in our hardware, it was called a cookie. We will get the source port. Okay, we will have the offload rule to set the source port ID to the cookie, so we can get it. Yeah, just in general from metadata, packet metadata. Okay, so later, then in the hypervisor, it can identify the source, the mbuf source port from mbuf to understand where it comes. Okay. So then for the fast pass, it is still the same. Once the application gets the missed packet, it will just offload the rules to the hardware. So next time everything works as before, same as before. Yeah. Okay, so then let's move on. So here let's see the flow rule tables. Okay, so yeah, this is the flow rule tables. So first we will have the FDB group 0 table. It just matches WAF, SAF, and path pattern. So that means all the packet comes from physical WAF. From WAF, SAF, and wire port will be captured by this rule. Then it will just jump to the offloading table, user's offloading table. Okay. Then user can set any offload rules. Okay. This should be configured by user. And in case it missed, okay, so that's the most important thing here. So in case the packet missed to applications, then before representer matching was disabled, while the representer matching equals to 1, it was enabled in the default case. So usually we will just match port ID and send the packet, stealing the packet to the relevant represent ISSQ. Okay, So if we disable the representer matching, in that case, we will upload new rules. So this is the optimization we did. In this case, we just match the port ID, pattern port ID, then the action, set the port ID to the mark, okay, the packet meta. So then it will just go to the representer, the uplink representer port, or maybe we can call it proxy port. It would be better, proxy port ISS table, since for now, the proxy port take over all the traffic, okay? Then in the general NICX ISS table, okay, we just match whatever we want, and then the packet goes to the relevant ISS queue, okay. So yeah, so just let's keep in mind, this is two big difference here. Okay, then what this optimization will brings, let's see. So in the queue preparation, before representer matching was disabled, in fact, we needed to prepare the queues and allocate them buffs for each representer port. But for now, since we disabled the representer matching, okay, then all the packet will go to the proxy port. So in that case, we only need to prepare the queues, set up the queues, and allocate buffs for proxy port, okay, only. Yeah. So this will save huge number of memory, okay. And now we have the simplified polling mode. See, so in that case, we just need to polling the proxy port. To every core will only polling one port's queue. So in that case, we just eliminated the cache miss. We are not calling the X burst for all the represent ports. Then the polling code, where the code will also be different. See, so before the optimization, so we needed to have this while to loop all the ports, okay, to call X burst, right, and then to handle the application logic. So think about that. And then after the optimization, in that case, in fact, we just needed to call X burst for the proxy port. We don't need to call for all the other ports, the represent ports. Yeah. And meanwhile, we can get to the source port ID directly from the FDR high. That means the packet meta. Okay. So finally, let's see the result. What brings the optimization will brings. Okay, so in the test model with 4 ports, 1 path and 3 WAFs, and 8 queues with 8 cores, 1 queue per core case. So user traffic generate, we use the user traffic generate to send 64-byte packet to the while port. Okay, so then comparing the memory consumption and the PPS, with the optimization, without the optimization, in fact, we will consume, let's see, a lot of huge page memory, like more than 800 megabytes. Then with this optimization, in fact, we are only using around, I'm not sure if you can see it very clear, okay, around 300, 332. Yeah. And the PPS, before the optimization, only with 4 port, it will degraded to 20 mega PPS. But meanwhile, if we decrease the X burst eliminate the X burst for the other represent ports, then it will increase to 27.5 mega PPS. Yeah. Okay, so I think that's it. Any questions? If no, then I think we're done. Okay, thank you.